Now let's see magnetic thermometer. Magnetic ions are doped into a solid substance to form a paramagnetic salt. These paramagnetic salts are utilized in magnetic thermometers as a sensing material and also as a refrigerant for electronic deviation cooling. A small percentage of magnetic ions are replaced with non-magnetic host materials atoms. As a result, as compared to the thermal energy, the interaction energy between magnetic ions or between magnetic ions and the host material's lattice is relatively low. When the temperature is decreased, however, the interaction energy approaches the thermal energy. The ordering of magnetic dipoles is no longer effective for temperature measurements if all of them are aligned below a specific temperature or when the interaction energy exceeds the thermal energy. As a result, the temperature at which all of the dipoles simultaneously align in the lowest limit for paramagnetic salt as a temperature sensor material. The partition function of the n-free dipole system was expressed by this equation. Here, x represents this value. Using the relationship of this, the magnetization of this system is calculated as follows. This equation. In the case of low magnetic field limit, x equal or less than 1, so V is small, then this condition is met, which is the condition of for most magnetic thermometers. So in this limit above equation, this equation can be rewritten as follows. In here we use the fact that cotangent hyperbole x can be expressed as this equation for x equal very smaller than 1. So we can get this equation. The magnetic susceptibility chi m over b is expressed using this m as follows. So magnetic susceptibility is inversely proportional to temperature. This is called the Curie law. We can see that if the magnetization or susceptibility is obtained, then amplification can be used to determine the temperature. Since electronic magnetic dipoles interact with one another or with host materials lattice and impurities, the Curie law does not hold in the electronic dipole system. We get the following relationship for the electronic dipole system when we consider magnetic interactions between dipoles and their surroundings. This equation. So this equation is known as Curie-Weiss law. Chi 0 represents the background effects, and delta represents Weiss constant. The Weiss constant is determined by the host material's crystal structure and the structure of thermometer sample. Magnetic thermometers are categorized as primary thermometers in principle, but chi 0 and delta should be determined via calibration. Thus, the electronic magnetic thermometer acts as a secondary thermometer. The temperature at which all magnetic dipoles spontaneously align is the lowest usable limit of magnetic thermometer. The spontaneous ordering temperature of electronic magnetic dipoles is determined by the density of dipoles. This is because as the number of dipoles increases, the magnetic interactions become stronger. As a result, by replacing magnetic dipoles with non-magnetic atoms, the spontaneous ordering temperature can be reduced even more. For example, paramagnetic salt CMN, cerous magnesium nitrite CMN, has a spontaneous ordering temperature of 2 millikelvin or 2 millikelvin. This spontaneous ordering temperature can be reduced to 0.2 millikelvin by replacing 95% of cesium ions with non-magnetic lanthanum. The electronic magnetic thermometer can be used to measure temperature in the range of millikelvin range. In the millikelvin temperature range, temperature resolution of 10 to the minus 10 can be achieved if a SQUID, superconducting quantum interface device, is used to measure the magnetization as shown in the figure. If we use the SQUID, then the resolution can be about 10 to the minus 10. This slide shows the shape of sample. Sample is put in one of static pairs. The sample, or this is a vacuum, and the sample is contacted on the plate at which temperature is measured. This table shows types of paramagnetic salt: CMN, CPA, FAA, MAS. For this CMN, magnetic ions is cesium. CPA is coal. FAA iron, and MAS mangan. Okay. And spontaneous ordering temperature for CMN 2 millikelvin, CPA 9 millikelvin, FAA 26 millikelvin, and MAS 153 millikelvin. Okay. The spontaneous ordering temperature is proportional to the density of magnetic ions since it depends on the interaction between magnetic ions. Thus, replacing magnetic ions with non-magnetic ions can lower the ordering temperature. We already discussed that. In CMN, the ordering temperature can be decreased below 0.2 millikelvin by substituting non-magnetic lanthanum for 95% of cesium ions. Paramagnetic sources are insulators with low thermal conductivity. The paramagnetic sample is made by mixing paramagnetic salt powder with grease for adhesive and copper or silver for high thermal conductivity, and then pressing the mixture into a desired form. We usually use the cylindrical shape. Temperatures around microkelvin are measured with a nuclear magnetic thermometer. The electronic magnetic thermometer and the nuclear magnetic thermometer operate on the same basic principle. Nuclear dipole moments, on the other hand, are 2000 times smaller than electronic dipole moments. As a result, the temperature measurements with nuclear magnetic thermometer will require a far more sophisticated technique. Curie's law, effectively explains the temperature dependence of magnetic susceptibility for nuclear dipoles. In this situation, the nuclear magnetic thermometer acts as a primary thermometer. Platinum is commonly utilized in nuclear magnetic thermometers as a sensor material. The technology of NMR, nuclear magnetic resonance, is used to measure modulation. The nuclear magnetic thermometer is depicted schematically in the figure. This figure. A pulse magnetic field, actually an electromagnetic wave's magnetic field, in the direction of the x-axis, in this direction, is applied to the platinum sample in the static magnetic field Vz is through the transmitter lead. So static field Vz is applied in this direction. High field, this is high field. P1 is much smaller than Vz. The magnetization vector of nuclear dipoles aligned in the static field's direction is then flipped to the x-axis by this pulsed magnetic field. However, after the pulse is removed, the magnetization vector of nuclear dipoles returns to the static field's original orientation. The magnetic resonance signal, FID signal, pre-induction decay signal is produced during this process. A receiver lead picks up this signal. You can determine the magnetization of the sample using this signal, and then use Curie's law to calculate the temperature. By applying excitation pulse, this pulse in x direction, at the Raman frequency to tilt the magnetization by small magnetization vector, actually by small angle theta. So we can detect the transverse magnetization. The receiver lead measures the induced voltage caused by this transverse magnetization. According to Curie's law, the temperature is inversely proportional to this voltage. So this voltage is proportional to the magnetization. So the Curie's law is that the magnetization is inversely proportional to temperature. So the temperature is inversely proportional to this voltage. This voltage is proportional to the modulation. This is a schematic figure for the animal measurement for the nuclear magnetic thermometer, and this figure shows the FID signal. FID signal is proportional to modulation, and as function of time, so is decay in this time and this value this value is so modulation, so we can detect this value, and this value depends on temperature. And this figure shows the schematic figure for temperature controller temperature controlling system. We measure the temperature using thermometer and setting temperature. So to compare this temperature with the setting temperature, and the heat is supplied to the heater to obtain the setting temperature.